In the last couple of videos, you learned about Newton's second and third laws. You might recall that Newton's second law states that force equals mass times acceleration, and that if you want to change acceleration, you must apply a force or change the mass. And you probably learned in Newton's third law that forces come in pairs. If I exert a force on object A exerts a force back onto me that is equal in magnitude and opposite in direction. So momentum works sort of similar to acceleration in that if I want to change acceleration, I must exert a force or change the mass. If I want to change momentum, I must exert an impulse. And remember that impulse is the product of a force times changing time. Now recall that Newton's third law states that forces come in pairs, right? So if I have two forces and they're internal to a system, they cancel each other out. Let's say that I'm driving my car and I want to push the car forward. Now, to push the car forward, the tires need to push on the ground and the ground will push the car forward. If I apply an internal force, like let's say I push on my steering wheel, right, I don't push the car forward because simply I push on the steering wheel pushes back on me, the forces cancel each other out, and the car does not move forward. Momentum works in the same way in that momentum is conserved and internal forces cancel each other out. So let's look at an example. Let's say I have a cannon that shoots a cannonball. Okay. So before I shoot the cannon and the cannonball together are at rest. Therefore, the momentum is 0. So initial momentum is 0 in this case. Okay. Now, after I shoot the cannon, it, moves forward at a certain velocity. And its momentum can be found by velocity times mass. And then also, the cannon moves backward at a velocity, and we can find the momentum because we can find the velocity, we can find the mass of that cannon. However, the momentum, the forward momentum, and the backward momentum are equal, and the cannonball system on the whole does not have any net change in momentum. So final momentum is 0 in this case as well. Essentially, the momenta of the cannon and the cannonball are equal in magnitude and opposite in direction. Remember that momentum is a vector, and they can be added together, and when they're equal in magnitude and opposite in direction, they cancel out, and net momentum is 0 in this case. So if no net force or net impulse acts on a system, then the momentum of the system does not change. And this idea can be stated as conservation of momentum, which is in the absence of an external force, the momentum of a system remains unchanged. So if I don't have any external forces acting on a system, momentum is conserved. So let's look at a couple examples using collisions to illustrate conservation of momentum. Okay, so let's say I have some ball A moving with an initial velocity, and it collides with another ball. Let's say they both have a mass of m. Okay. So it collides. What ends up happening after the collision, so this is before, is the first ball stays at rest, and the second ball moves forward with the same velocity that the first ball had. Okay? So we see that the momentum in the before is, let's just call this velocity v. The momentum before is mv, right, plus the momentum of the second ball, which is m times 0, because it doesn't have velocity. So that's just equal to mv. And the momentum after is momentum of the black ball, which is m times 0, because now it's at rest, plus the momentum of the red ball, which now is moving at the same velocity that the black ball was moving at. So that momentum is m times v, and that's also equal to mv. So we see that the momentums are equal before and after the collision. So we see that momentum is transferred from the black ball to the red ball. In an elastic collision, and an elastic collision is defined as a collision where neither of the objects are permanently deformed and heat is not generated, meaning that no energy is lost to the surroundings. The momentum before will equal the momentum after. In inelastic collisions, where some energy is lost to the surroundings or the objects are deformed, then momentum before doesn't necessarily equal momentum after the collision. Okay, so let's look at a couple different examples of elastic collisions. Let's say that I have, again, the black ball moving at some velocity, and it has a mass m. And let's say now that this red ball is moving directly towards it, and it has the same mass m, and they have the same initial velocities. And let's say that they collide. So they collide in the middle, so this is before. So what ends up happening after is that the black ball moves in the opposite direction with the same velocity, and the red ball moves in the opposite direction with the same velocity. Okay, so again we see that momentum is conserved because mass times velocity before will equal mass times velocity after. So let's take what we've learned about elastic and inelastic collisions and apply it to the bouncing ball. Okay, so if I throw a ball on the ground must exert an impulse to stop the ball. Now, if the ball is to bounce back up, the ground must exert another impulse to kind of throw the ball back up into the air. So why doesn't the ball reach the same height it had initially? That's because some of this momentum is lost to the ground in the form of heat. And actually, when you bounce a ball, the spot where the ball hits the ground will be slightly warmer. So momentum in that case is lost to the surroundings, and that's why the ball doesn't necessarily bounce up to the same height. So, if you continue to bounce the ball, eventually it kind of does something like this. Because after each bounce, some energy is lost. Okay. So let's now consider what happens in inelastic collisions. An inelastic collision is a collision where two objects collide and they end up sticking together to form one object. So think of if I am driving a train and I smash into the second train and now I'm attached to that train and we're moving forward together. Okay, so an important idea to remember when solving these kind of problems is that net momentum before the collision must equal net momentum after. Okay. So let's consider an example. Let's say that I have one train with a mass of 20 kilograms. It's a light train. And it's moving at a velocity of 5 meters per second. And let's say that I have another train further up the track that has 0 velocity. and also has a mass of 20 kilograms. Okay, what is the final velocity of these two trains after they collide if it's a perfectly inelastic collision, meaning that they stick together? Okay, well, we know that net momentum before must equal net momentum after. When we talk about net momentum, we're talking about the momentum in the whole system, and this system is comprised of these two trains. Okay, so momentum before is the momentum of the first train, which is 20 kilograms times 5 meters per second, plus the momentum of the second train, which is 20 times 0, so that's 0, will equal the net momentum after the collision. So after the collision, these two bodies are moving as one, so their mass is 40 kilograms. And velocity is what we're looking for, so I'll just write v. Okay, so solving for v, 20 times 5 is 100. And I divide by 40 kilograms. I get that velocity is 100 over 40, which is the same as 5 over 2, or 2.5 meters per second. Let's consider another interesting example with inelastic collisions. So let's say that I have this ball, this black ball again, and it has a mass m. Let's say it's moving at an initial velocity of 3 meters per second. And let's say that I have another ball, I'll do a different color, with the same mass m, moving at 3 meters per second, but in the opposite direction, so we're going to call this negative 3 meters per second. We'll define the leftwards direction as negative and the right direction as positive. Okay, and let's say that the balls collide and they stick together, so it's a perfectly inelastic collision. So let's say we want to figure out what is their velocity after the collision. Alright, so we know that net momentum before the collision must equal net momentum after the collision. So net momentum before the collision is the momentum of the black ball, which is 3m, plus the momentum of the red ball, which is negative 3m. So it's the momentum before the collision, and we know that it must equal the momentum after the collision. Well, the mass after the collision is 2m, because the balls are now stuck together, and velocity is what we're solving for. Okay, so if I simplify the left-hand side, 3m plus negative 3m is 0. Therefore, the velocity after the collision is 0 meters per second. So they collide, and they stay in place. They're at rest. So we've learned about the conservation of momentum, which can be defined as in the absence of an external force, the momentum of a system remains unchanged. And we've also learned about types of collisions, including elastic, where no energy is lost, or there are no deformities. Inelastic, where some energy is lost, or there are some deformities. And then perfectly inelastic, where the objects stick together. So we will use these principles to solve momentum problems in the next video.